Okay, so we have studied line integrals a little bit. And what I'd like to do now is to show you one of the, if not the most important application of line integrals, and that is the application of work. Now, in general, work is done by a force when it moves an object, right? But what's more important to you as, say, a scientist or as an engineer, it is you're often going to need to be able to calculate how much energy is going to be needed to perform some various job, right? So, I mean, if you want to know how much energy you need for a crane to lift an object, or how much energy you're going to need to propel a rocket, or how much energy you're going to need to compress a spring, or for some tractor and trailer to haul a load. But what we're going to see, well, actually, I'll tell you what I'll build us to get there. So I read, generally work is done by a force when it moves an object. And obviously that force, it could be a constant force on a straight path. And in scenarios like that, work is fairly easy to calculate. Work is just calculated by, the force multiplied by the distance. So it's possible the force is constant, a constant amount of force being placed on an object on a straight path. It's possible that the force is variable along a straight path. Right? So in that case, let's think about if you're pushing a refrigerator. It's possible that you're pushing a refrigerator on a straight path with a constant force the entirety of throughout the movement, or maybe sometimes you're pushing harder than other times. So it could be variable along a straight path. And we found that back in probably chapter 7, we found that for variable force along a straight path, work can be calculated as the integral from a to b of some force, right? And so, I do hope that you understand that this is just another way of thinking about force times distance, right? You're just thinking of it now as like an accumulation function, where you're accumulating work as you go. So as this refrigerator moves from point A to point B, you had, let's say, a lot of force in the beginning, and then a little bit of force, and then a little bit of force. And you're accumulating force as it moves, and the accumulation, the total amount of work, can be calculated here. So we also found that you can use dot products and projections, right, to calculate force. And we did a little bit of work on this in chapter 12 when we were just introducing vectors, and we found that work can be calculated as force times some vector, right? And this allowed us to start thinking about start thinking about the direction in which we are applying the force, right? So back to the refrigerator. So if you're applying the force along a straight path, or maybe it's the location of the refrigerator is such that you can't really get your hands on it like that, and maybe you have to apply your force at an angle. And now what we want to do is we want to shift our attention to, like I said, to one of the most important applications of line integrals, and that's really is going to be finding work of an object moving in a force field. So the idea, so again, now a force field is just a vector field, and you can see that. So when you have circular paths, so for example, circular paths like this, you can see that the magnitude of the force on the circular paths are the same, right? So you can see that the magnitude of the force here is the same as the magnitude of the force here and so forth. That's this is an inverse square force field, right? This is a vector field, but again, on circular paths, the magnitudes are going to be the same on that throughout that path. But now, when you have an object moving on a curve, right? So like take, for example, this parabolic path. So if you have an object, moving on a curve, notice that the force vectors, or the magnitudes of the force vectors, are not the same throughout the entire path. Right, you can see that the magnitude of this vector is different than the magnitude of this vector is different from the magnitude. So what we want to be able to do is come up with a way of calculating the accumulation of force, only now we're going to have some object moving on some curve, some path through a vector field. Okay, so to kind of build us up to where I want us to be, let's see, in this case, is the path of an object in some field, right? So some object, this is the path of motion in some vector field. Now, the way we want to kind of think about this is, if you want to determine the work done by the force let's just talk about it at a particular point, right? The work done by the vector field at a particular point. So what you have to imagine is that you have all of these. If you're in a force field, you have all of these forces that are being applied. Okay? So all of these forces are being applied, but we only care about this particular path because we have this object moving through a force field, but on this particular path. Now, if you care to let me switch back to my stylus. So if you care to determine the work done by the force, it should make sense that you're only going to have to consider the part of the force field that is acting in the same direction that the object is moving. Or the opposite direction, right? So if you had force vectors going this way, you would have to consider that. But we don't have to consider forces that are acting on the object moving in different directions than just. We only have to consider the forces operating on the objects moving the same direction, or obviously the opposite direction. So all that means is using the idea of that dot product, that idea of that projections that we learned back in chapter 12. That would mean that, let's just talk about a particular point, that if so at this particular point on your path, you can just consider the dot product of basically the dot product of what, I guess it's worth discussing. So it's going to be the dot product of the force and the unit tangent vector. And we know that the unit tangent vector is going to always point in the direction of motion. So what we're I don't know why I did that. So what we're doing here is we're considering, the dot product of the force and the unit tangent vector, and basically in the direction of motion. So it ends up looking like this. So if you, I hope I'm using the physics language correctly here, but mathematically, as long as your arc is small enough, then you can find the amount of work being done at that point by simply calculating. It would basically be force times distance, which would end up being the dot product f of t times the length of that small little arc. But we don't want just the amount of force on some tiny little arc, right? We want to know if that object's moving through that path, how much force has accumulated, right? What is the totality of force on that object? To do that, you're going to need an integral, and in fact, you're going to need a line integral. Now, let's just recap. This is the line integrals that definition of line integrals that we've been using for a curve in space. And just notice that you have your force field, and then you have, which is right, force times distance, right? So if force times distance, and then you're daydreaming. I know you are. This is your force. This is your distance. Work is just force times distance, and this is your accumulation. Okay? So the good news, if you allow for some good news, the good news is, so we would start off, the way it would be, we would start off is, we would have our line integral, and we would have our dot product, f dot t. Now, and then we would need our square root. Well, let me see if I can do this a little bit better. So remember that back in chapter 12, we would think about the magnitude of r prime as being represented. The magnitude would be the distance of the vector. So this entire portion right here is just the magnitude of r prime. Right, so r prime of t. Which is good for us because, so that's going to be times, let me write times not as, so you don't confuse it with the dot. So times the magnitude of r prime of t. The good news is, think back to our definition of the unit tangent vector. And our definition of the unit tangent vector was r prime of t divided by the magnitude of r prime of t. So some things are going to cancel out here that make our life a little bit easier. So if you can imagine me substituting r prime of t over magnitude of r prime of t here, you can see how the magnitudes are going to cancel out. And I'm going to write it just so that you have it in your notes. So then it ends up looking like the following. So still a dot, but now it's going to be dot r prime of t divided by magnitude of r prime of t times magnitude of r prime of t dt. So these magnitudes are going to cancel out, and let's see what's left at that point. So for the total amount of work, we're going to have the line integral of your vector field, your force vector, times just r prime of t dt. And by times, I do mean dot product. Okay. So that is what is produced for you here. I just wanted you to see where it came from so that you're just not accepting another math formula to add to your collection of math formulas that you have at this point. The only thing is, so let's kind of jump into a question. So if you want to, say, calculate the work done by some force field. Now, so here's our force field. And we want to calculate the work done by this field on a particle as that particle moves along the path of a helix, right? So this is the path of the particle. And the path is given to us. And since we're going to be accumulating work to find the total amount of work along that path, we do need a starting point and a stopping point. So from the point 1, 0, 0 to the point -1, 0, 3 pi. So from here to here, how much work, total work, is accumulated. Okay, so let's go ahead and the first thing that you're going to want to do, you are going to want to build your integral. I'm going to go ahead and write the things that are known, because the first part is key. Okay. And now, let me go ahead and under that I'll write r of t. Okay. So remember, this is the goal. We want to be able to plug in, because we want to be able to calculate work. So we got our line integral. And it's the dot product of f and r prime of t dt. And let me now tell you the most common mistake. So a student grabs f and then plugs here, and then grabs r and takes the derivative, the derivative of r, but plugs f here, then r prime here, and then they start integrating. And wait a minute. This force field is in terms of x and y, right? X, y, z. This is rectangular. You can't have rectangular force and then be integrating with respect to a parameter of t, right? So you have to parameterize the following. So how do you go about doing that? Well, let me kind of scoot some things down here. So we know that when we want to think about, when we go to plug in, we're going to think about x of t, not x. So we need x to be a function of parameter t, y to be a function of parameter t, z to be a function of parameter t. So the question is, what do we plug in for x, y, etc.? Well, let's think about it. If you jump to your space curve, this will tell you x of t, y of t, z of t. So this cosine of t is your x of t. This sine of t is your y of t. And this, let me write t a little bit better. So it doesn't look like a plus symbol. Okay, and this is your z of t. So in this case, what's going to happen is we're going to take cosine of t, plug it in for x. We're going to take sine of t, plug it in for y. Now, there is no t variable associated with k, so in that case, as soon as we plug in cosine of t, sine of t, we will have a function in terms of t. So I'm going to just draw you a picture so that you have it for your notes. Okay, and we want to plug in. All right, so let's build. We'll go ahead and start to build our work function. So we got the line integral of c. Once I've started that substitution process, that's now going to be negative 1/2 cosine of t, I direction. And that's going to be minus 1/2 sine of t, j direction. And then it's just going to be plus 1/4 in the k direction. Dot, all right, dot what? Well, it's going to be dot r prime. So in this case, r prime of t is going to be negative sine of t, I, plus cosine of t, j, and that's just going to be plus k. So this is going to be going here. So negative sine of t, I, plus cosine of t, j, plus k. I'm gonna copy this since we're going to be going to the next page anyway. Let me just copy this, paste it on the next page where I have a little bit more room. So plus, let me make sure I wrote a plus symbol first off. Should have been a minus symbol. So minus cosine of t, no, it is plus, right? Because it's a derivative, sorry. So plus cosine of t, j, plus k. So we're going to need that dot product of that. And then we want to integrate with respect to t. Just notice that we have not set up our bounds. So that's what we want to discuss now. So the bounds for our integration also need to be in terms of t. Okay, because if you're going to integrate with respect to t, then you're going to want to plug your bounds back in for t. So we need our bounds to be in terms of t. So what we're going to do is let's start with our the points that we're given. We're given 1, 0, 0. And we're given the point, so that's the starting point, and the stopping point is -1, 0, 3 pi. And I'll label these sub-2s, sub-1s. Okay, so somehow we have to take this information and create bounds, but the bounds must be in terms of t. So recall that x of t was just cosine, y of t was cosine of t, y of t was sine of t. But recall that z of t is equal to t. All right, so recall that z of t is equal to t. In other words, if you were to just think about our component of k as equal to z, then z is equal to t. So all that means is we can find our bounds by just looking at the z values. So we're going to be going from 0 to 3 pi. All right. All this tells us that t is bounded between 0 and 3 pi. That's what we need. So there we have it. So what I'm going to do is I'm not going to write all of that out. But the work is going to be, we're going to have to integrate from 0 to 3 pi. And then I'm going to be taking the dot product of these two vectors. So remember, dot products are fairly easy. It's just going to be let's see here. So it's going to be -1/2 cosine of t times negative sine of t, then -1/2 sine of t times cosine of t. And then we're going to have 1/4 times 1. So it's going to be the sum of those. So what's that going to look like? Well, that dot product is going to look like the following. So it's going to be negative, let's start with the I components. So if you have -1/2 cosine of t times negative sine of t. So that's a negative times a negative. So that's going to be +1/2 cosine of t sine of t. All right. Remember, a dot product's not a vector, so we're not going to write the j's and the i's, j's in case. So now you have a -1/2 sine multiplied by a positive cosine. So that's going to be a -1/2 cosine of t sine of t. And then finally, you just have 1/4 times 1, or just plus 1/4. Well, these will cancel. If you have a half cosine sine t, and you take it away, then you don't have any. You have 0. They cancel out. So at that stage, you're just left with the integral from 0 to 3 pi. The only thing left is 1/4 dt. So easy enough. Integrate. So that's 1/4 t from 0 to 3 pi. And start plugging back in. And what you get is 3 pi over 4. So you were asked to find the work done by that force field on a particle as it moved over a path from one point to the next point, and this is the total work done by that force field over that interval. I will see you guys in the next section.